Hello, welcome to this presentation of the E-B thermoelectric effect. My name is George Levy. I am with the company Entropic Power in Irvine, California. The E-B thermoelectric effect is remarkable because of its carrier transport mechanism, which is charge parity time symmetric. It is unlike other effects which depend on a temperature gradient and phonon drag to produce a current. It is purely electromagnetic and relies only on the configuration of the electric and magnetic fields. I will cover the following topics: the E-B drift when mobility is infinite and when it is finite, compliance with the second law, and fabrication of a device. First, let me make a distinction. The E-B drift is a well-known electromagnetic transport mechanism that relies solely on the electric and magnetic fields. The E-B thermoelectric effect utilizes this drift to produce a useful current that can drive a load. Before discussing the full-fledged E-B drift, let's look at a simpler case in which a magnetic field is applied to a high mobility material. Carriers in the material, such as electrons, follow circular orbits. When an electric field is added perpendicularly to a magnetic field, particles accelerate as they go down their potential energy gradient and decelerate as they go up. This causes the radius of curvature of the path to increase at the bottom and decrease at the top. The circular orbits become cycloids. The cycloids can be viewed as circles whose center drift with velocity v in the direction of the cross product perpendicularly to both fields. In fact, Vx is equal to the ratio of Ey to Bz. When mobility is infinite, the drift velocity is a ratio of the electric field to the magnetic field. It is not a function of the charge or mass of the particles. And unlike in other thermoelectric effects, the drift is not a function of a temperature gradient. Electrons and holes drift in the same direction with the same speed, and when their concentrations are equal, their contributions to the current cancel out. The net output current is zero and there is no thermoelectric effect. However, as we shall see, this is not generally the case. In real semiconductors, electrons and holes have finite and different mobilities, as well as different other transport properties such as concentration and effective masses. These differences make the E-B thermoelectric effect possible. In real semiconductors, electrons and holes have different transport properties. Their drifts fall midway between two limiting cases, shown on the left. Case 1 is infinite mobility, in which particles drift with velocity Vx perpendicularly to both fields. And case 2 is near zero mobility, in which particles drift down their potential energy gradient. The box on the right shows the intermediate case, in which electrons and holes drift with different speed in different directions according to their mobility and effective mass. Electrons drift diagonally down and to the left. Holes drift diagonally up and to the left. Their contribution to the current do not cancel out. A net output current is produced. What is the source of energy driving the E cross B effect? Unlike other thermoelectric effects, the E cross B transport mechanism is a field configuration, not a temperature gradient or heat flow. Ambient heat, the only available energy, must be converted to electrical energy. Does this effect violate the second law? The short answer is no. The law is not violated. How is this possible? The reason lies with the Crosby drift transport mechanism, which is charge parity time, or CPT symmetric. Time symmetry is broken at the macroscopic scale by the particle velocity distribution, which is biased by the drift velocity. In contrast, the second law, as expressed in the H-theorem, assumes time symmetry and unbiased distribution. Therefore, the A cross B effect is not covered by the theorem, and there is no logical inconsistency in the laws of physics, as shall be further explained in the following slides. Now let us discuss how the E cross B effect complies with the second law. The second law is a vast topic that applies to a huge range of fields, from biology to black holes. Unlike other physical laws, it has remained untouched since its inception in the 19th century. As Albert Einstein said, thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown within the framework of applicability of its basic concept. Einstein's quote is double-edged. It does mention the universality of the law, yet it alludes to the framework of applicability of its basic concepts. What is this framework of applicability? Two famous scientists, Lars Onsager and Ludwig Boltzmann, provide a few hints. As we shall see in next slides, Onsager suggests that the law may conflict with magnetic fields, and Boltzmann hints that the law only applies to time-symmetric systems. First, let us discuss Onsager. Onsager received the Nobel Prize for conceiving of reciprocals. He found that in the presence of magnetic fields or rotation, reciprocals would lead to a violation of the second law. He assumed that the law could not possibly be broken under any condition. In other words, he did not consider the framework of applicability of the law to be an issue. Therefore, his solution was simply to restrict reciprocals to an environment devoid of magnetic field or rotation. He had no other reason to do so but to avoid a conflict with the second law. Boltzmann was one of the founding fathers of thermodynamics. One of his signal achievements was the H-Theorem, which is a proof of the second law. This theorem states that the entropy of an isolated system can never decrease. In other words, ds by dt is always equal to or greater than 0. In his proof, however, he had to assume what is known as molecular chaos, that at the macroscopic scale, time is symmetrical, collisions are indistinguishable from those seen in reverse time, and the velocity distribution of particles remains unbiased and symmetric in orientation. This assumption limits the applicability of the theorem and hints at a restricted coverage of the law. The E cross B effect oversteps limits set by Onsager and Boltzmann. It includes a magnetic field outlawed by Onsager in his reciprocals It is CPT symmetric and therefore breaks the time symmetry assumed by Boltzmann. It adds a drift velocity bias at a microscopic scale to the velocity distribution, thereby violating an assumption made in the H-theorem. Therefore, the E cross B effect falls outside the coverage of the H-theorem. There is no logical inconsistency and no violation of the second law. The E cross B effect simply bypasses the second law as defined by Boltzmann. The E cross B drift is a function of the figure of merit and can be turned on or off by adjusting Fm. Therefore, an E cross B effect system can be built in two parts: a forward path with a figure of merit about equal to 1, favorable to the drift, and a return path with a figure of merit near 0, unfavorable to the drift, but that can carry a conventional ohmic current. Changing Fm requires changing mobility, that is, increasing it in the forward path and decreasing it in the return path. To compensate for the change in mobility, yet keep conductivity constant around the loop, the product of mobility and concentration is kept constant. Note that the electric field and the magnetic field can also remain constant around the loop. In this system, the forward path acts as the battery and the return path as a load. The current produced by the forward path drives the load in the return path. Here is an example of a thermoelectric effect device. The magnetic field can be produced by a permanent magnet, and the electric field by capacitor plates, electrets, ferroelectrics, doped surfaces, or junctions. This device operates on ambient heat. I will leave to your imagination the benefits and advantages offered by this technology. This concludes my talk. I welcome any thoughts, comments, or questions you might have.